of our morning session, Professor Igor Burban, University of Paderborn, Germany, with talk Algebraic Geometry of the Fractional Quantum Hall Effect on a Torus.
Yeah, thank you very much and good morning. So I'm just trying to share my screen, but I am not succeeding somehow. Okay. No, it's now better. Can you see it?
Yes.
Okay, so now let me make a full screen. Okay, it's really my pleasure to give a talk at this conference. And there is some physics behind of it, but this physics uses algebraic geometry. I got fascinated by the subject a few years ago, and now I would like to share my fascination with you. So the oversimplified picture of the quantum Hall effect is the following. So here you see two-dimensional sample which is conducting, and we have a current going, let's say, from south to the north. And it is important that the sample is basically two-dimensional. Now, assume that the sample is put into a magnetic field, which is perpendicular to the sample. So it is indicated by this letter B. And now, well, electrons moving in my sample are affected by the Lorentz force. So which has as an consequence that, well, let's say there are more electrons on the west than on the east because of the magnetic field, and we get an induced voltage, so an induced electric pressure. So, and if we connect both boundaries of our sample by conducting material, so we would get a new current. And now we can consider the physical quantity, so the quotient of our initial current I by the induced voltage appearing from the magnetic field, which is called Hall conductance. And the inverse value of the Hall conductance is Hall resistance. Now, what is special about this value? It was a striking experimental discovery of German physicist von Klitzing, who observed that in low temperatures, so near 0 degree Kelvin, and in the presence of very strong magnetic field, the value of Hall conductance or Hall resistance is not arbitrary. So it takes actually integral values of a very special constant, which is nowadays is called von Klitzing's constant. So here in this picture, so there are a lot of decorations, but important is this red one, which indicates possible values of the Hall resistance as a function of the magnetic field. So and this picture shows that values are somehow discrete. And the question was, what is actually a model? What is an explanation for that? Because when it was discovered in the early 80s, it was quite an unexpected and striking discovery. Quantum Hall effect had a long and glorious history, which is not yet finished. And in particular, for this discovery, he got a few years later a Nobel Prize in Physics. 2 years after discovery of von Klitzing, other experimentalists, Zu and Störmer, discovered that in very pure samples, the value of Hall conductance can take also fractional multiples of von Klitzing's constant. So, and fractional multiples are quite not arbitrary. And the first and partial theoretical explanation was given by Robert Laughlin, and again, 3 of them got several years later, so 15 years later, Nobel Prize in Physics for this work. Quantum Hall effect was originally observed at very low temperatures, so near 0 Kelvin, but another striking experimental discovery, so more recent by Game and Novoselo, was that the fractional quantum Hall effect exists also at room temperatures in material called graphene. And they got for this discovery again Nobel Prize. The most recent Nobel Prize for theoretical work was awarded in 2016 to Taurus, Haldane, and Kostolitz, for not only for the fractional Hall effect, but let's say for the transfer of ideas of topology to condensed matter physics. And it's one yet more Nobel Prize for this research. So of course, there are many scholars who got also other important awards. So let me just sum up that in condensed matter physics, fractional Hall effect is considered as one of the most important and striking discoveries in the past decades. So now let's proceed to mathematics and to mathematical models. And fractional quantum Hall effect is about mathematics of many particle systems, but it's natural to start with just one particle and some quantum mechanical motion of it in a magnetic field. And basic quantum mechanics tells us that the motion is described by some self-adjoint operator. So I want to consider a motion in 2 dimensions. And we have an operator L, a magnetic Schrödinger operator, which has some domain of definition. And it's important and quite significant that our dimension is 2. So in higher dimensions, phenomena are different, but in 2 dimensions, the spectral properties of L were studied by the famous Soviet physicist Lev Landau. And maybe it's also of interest to Ukrainian audience of my talk. So Lev Landau was born in Baku in Azerbaijan and started to study physics there. Then he continued in St. Petersburg. And he was one of few Soviet scholars who were allowed to study abroad, so in particular in Germany. And Landau spent his time in Germany very efficiently. So he was several years in Göttingen and also learned very early about development of quantum mechanics. And in particular, in the year 1930, he made a work which is now contained in any textbook in quantum mechanics. And there is a very elegant derivation of this result, saying that the spectrum of this operator is actually discrete. So it is not so in dimension 3, and it is not so if our magnetic field is 0. So if B is 0, then we have a continuous spectrum, but in the presence of magnetic field, the spectrum is discrete. And if we ask about the ground state, so the eigenspace to the lowest eigenvalue, then there is a very concrete description. So there is some exponent multiplied with an analytic function on the entire plane. And everything is considered as a subspace in L2 of R. So this exponent also guarantees convergence. And well, the convention is that my constant B is positive. because otherwise everything has to be modified. So it's a starting point. And as particular observation, so exponent times polynomial is an element of the ground state for any value of k. Now, if we speak about many particles, so basic quantum mechanics says that we have to take the tensor product of Hilbert spaces for each individual particle. And if we have no interactions, that here is an operator describing the motion of n particle system, and knowing the ground states or even eigenstates of one particle, so we can say everything about n particles. But we ignore here interactions between particles, and interactions are important. Now, one of the contributions of Robert Laughlin, and as I mentioned, Laughlin later got a Nobel Prize for his work, was the following, that for the system of interacting particles, it is natural to consider the following wave functions phi, independence of m, and m, well, is some number, well, which is reflected by the physics. So what is this function phi m? So we have some prefactor, which is holomorphic. If m is odd, it's also antisymmetric, and it's important if we speak about electrons, because they have to satisfy fermionic statistics. And this function phi is an element in the ground state of my n-body magnetic Schrödinger operator without interactions. But now if I have interactions, and let's say they're described by some potential W, then it's actually mathematically not so clear what to do. And there are only few cases when we can give explicit formula for eigenstates, for the ground states. So mathematically, it's challenging. But Laughlin made the following suggestion. So he said, well, there are interactions. So physics tells us that they are here, they cannot be ignored. But let's say if we take this prefactor, then the obtained wave functions is a very good approximation of true wave functions we actually have in physics. And well, this observation so may it look like innocent, but it was quite striking for the further development. Well, it was maybe some overview for what is going on the plane, but I want to proceed to other models. And I also want to tell you that algebraic geometry have something to do with what I'm talking to you about. And now let's speak about the complex torus. So the complex torus is a quotient of the plane modulo a lattice. And it is convenient to assume that the modular parameter tau is such that the imaginary part of tau, well, so it's non-zero anyway, but actually I wanted to say that imaginary part is positive. So later on it will matter. As the next piece of data, let me consider a holomorphic function phi. And the special thing about phi is that it is periodic. So it has a period 1. Now, let me introduce two further parameters, integer k and continuous parameter xi in my plane. And after making these choices, I introduce a new function psi, well, which is expression of what I have introduced you before. So there is some prefactor depending on xi, and I have a case power of my function phi. Psi is also periodic with period 1. And now I can tell you what is a holomorphic line bundle on a torus. So a holomorphic line bundle on a torus is denoted here in my diagram as LKXI. So what is it? So if I take the product of C with V, V can be actually any vector space. So for line bundles, it is one-dimensional. So if I project this product on the first factor, then the phi bar of each point of C is this vector space V. But I want to construct a line bundle on my torus. So, and for that, on the product C times V, I introduce an equivalence relation, which is provided by the rule below, and which is given by the function psi, which is called actually automorphy factor. And the special shape of psi guarantees that this is indeed an equivalence relation. So now it is not so difficult to observe that the phi bar over each point of my torus can be again identified with vector space V. So in this way, I get a holomorphic line bundle on my torus E. And this torus has degree K. So any line bundle on a Riemann surface has a degree. And here is actually a picture of a line bundle. So summing up, taking K and choosing a continuous parameter psi, I get a holomorphic line bundle. And it is a certain statement which asserts that any holomorphic line bundle of degree K is of this form. So it's first basic theorem about line bundles on a torus. Now, having line bundles, I can speak about its sections. And let me start with smooth sections. Smooth sections are nothing but smooth functions with these quasi-periodicity conditions. So this statement follows immediately from the definition of my line bundle L, KXI, via factors of automorphy. Next, my line bundle carries another structure, namely a Hermitian metric. So what does it mean? So I want to say that if I have a local section, then over each point, the phi bar has a length. So what does it mean that the function h defines such a metric? So having any global smooth section f, I can consider the following function on E, which involves the chosen function h. And the choice of h is special, guaranteeing that the function itf is indeed a function on a torus. To be a function on a torus, we have to make sure that it is periodic with respect to shifts by with respect to a lattice, and it is indeed the case. And it means that any local sections and also any global sections, well, so we can speak about lengths of sections at any point. So it is what the choice of Hermitian metric on the line bundle actually means. Right, to continue, let me sum up. So we have a holomorphic Hermitian line bundle of my torus. And we spoke about its smooth sections. And since we have chosen a Hermitian structure on L, so we have scalar products in fibers, and having two global smooth sections, well, we can actually assign a scalar product of them. So we take a function assigning to Z the scalar product of values of these functions in Z. So we get a function, and then we multiply it with the volume form on my torus and get the differential form, which can be integrated given a number. So actually, it's a general fact that if we have a Hermitian complex line bundles, and global sections carry a Hermitian scalar product. And if we have such a scalar product, we can also now speak about square integrable sections, not necessarily smooth. In the same matter, how we go from continuous functions or smooth functions to L2 functions. And we get the Hilbert space. So actually, I want to come to some quantum mechanics again. So for quantum mechanics, I need a Hilbert space. Now, the next observation is that I have a well-defined linear operator, which is given by the Cauchy-Riemann operator, del bar. The point is that since this factor of automorphy is holomorphic, del bar kills it. And because of that, the operator del bar respects this quasi-periodicity conditions global functions actually satisfy. So I have a well-defined linear operator. And another exercise to do is that this operator admits an adjoint operator, given again by differentiation, and it involves my chosen Hermitian metric. So now I can construct Schrödinger operator applying del bar and coming back by adjointness. And with this operator L, I want to work in what follows. So again, to sum, I start with a line bundle on a torus. I equip this line bundle with Hermitian metric. And I constructed a Hilbert space and some operator acting on it. And this operator is known in mathematics, and essentially it coincides with a so-called holomorphic Bochner-Laplacian of a Hermitian holomorphic line bundle. So it is actually something very canonic and very natural from the mathematical point of view. And now the statement is, so it's a postulate, an axiom, that the quantum mechanical motion of a charged particle on my torus, in the presence of a constant magnetic field, is described by this operator L. This operator L is actually having very good properties, so it is self-adjoint, but on compact spaces it also has only a discrete spectrum with finite dimensional eigenvalues. So it's a very nice self-adjoint operator. Well, it's let's say it's a postulate, but there is some mathematical evidence for that, which is best given by the theory of geometric quantization. And the idea behind is that one can speak very rigorously from the point of view of classical mechanics, how we think about classical motion of a charged particle in a magnetic field. And then there is a procedure saying how to quantize such a model, well, leading to the conclusion that the quantum mechanical motion is described by such an operator L. So for us, it's important to have a good control of the ground state of this operator. And by the very construction of L, one sees that the ground state, so since this operator is positive, is a kernel of del bar. So by construction, it's well, obvious. And the conclusion is that if K is positive, then the space of holomorphic sections of my line bundle can be identified with the ground state of my magnetic Laplacian L. And It's a reason why algebraic geometry does appear, well, in this model. So it's actually the link. On the one hand side, we want to speak about the ground states of some self-adjoint operator, but on the other hand, well, we have holomorphic sections of a holomorphic line bundle on the torus. And Riemann-Roch theorem says that the space of holomorphic sections has dimension k. All right, so what is this space? So the key point is that this space also has a distinguished basis given by theta functions. Now let me recall this theory of theta functions. So it's very classical and very beautiful part of the classical function theory. So again, let me start with parameter tau with positive imaginary part, which defines a lattice in a plane. Now, in general, if we speak about theta functions, one has to speak about theta functions with characteristics. And these are two real numbers, A and B. And after making these choices, we can consider a series, and important is dependence on Z. But looking at this series, one can conclude very quickly that it converges for all values of Z. And the reason actually is that, well, T, the imaginary part of tau, is positive. And if we really write what is the absolute value of each summand, we see that, does not matter what Z is, this series are converging very rapidly. And formal manipulations with series also allows to conclude very quickly the following two quasi-periodicity conditions. In particular, one can show that theta function as a function of Z has a unique and simple zero at the point pi psi modulo the lattice. Now, assume we want this pi psi should be 0. So it means that A should be 1/2 and B should be 1/2. It's a very special case. And in this case, we speak about the so-called first theta function of Jacobi. And this theta function has a unique simple 0 at the origin, and moreover, it is odd. And it will be important in the story I want to tell you next. But so far, these are standard results about theta functions. Now, the quasi-periodicity of these theta functions allows us to think about them as sections of line bundles. So again, let me repeat that to construct a line bundle on a torus, we have to make choices. Now, k is a positive integer and psi is a continuous moduli. So I told you how to define holomorphic line bundles on one-dimensional complex tori. Also explains that global sections of L are holomorphic functions satisfying these quasi-periodicity constraints. And now, from what I told you, it's not difficult to conclude that the vector space WKXI has this distinguished basis. So I explained that the dimension of this space is K, the degree of line bundle. And there is a distinguished basis given by theta functions with characteristics, which can be checked just looking at the corresponding quasi-periodicity properties. So now let me proceed to the model of the fractional quantum Hall effect on a torus. And it is a work of Haldane and Rezai from the middle of 80s. The starting point is again that we have some magnetic Schrödinger operator, and I explained you that the ground state of it can be identified with the space of holomorphic sections of a holomorphic line bundle. Now, if we want to speak about many particles, so let n be the number of particles, and well, there is another parameter m. And before giving you the ansatz of Haldane-Rezai for wave functions, Jacobian theta function. So a special thing about this function dm is that it vanishes with the order m along all partial diagonals. So recall that theta has unique symbol 0 at the origin, and because of that, this function vanishes with order m along of each diagonal. So it will be important in what follows, but I'm not yet done. So now let me define for any value j between 1 and m the following expression involving now theta function with characteristics. And I multiply this function phi jc, c stands for center, with well, this discriminant dm. And let me consider the linear space spanned by these m constructed functions of n variables. So the first observation we could make is that these functions have symmetry. So they are symmetric if m is even. So they are symmetric because, well, sum of arguments is symmetric. And the function here in parentheses is actually anti-symmetric, but even m kills and make it symmetric. And in the fermionic case, this function is anti-symmetric. So this space was introduced in the work of Haldane and Rezai in 1985. So now I have to give you another explanation. Why did they care about this function? So recall that Robert Laughlin made the following ansatz for wave functions of electron system on a plane, and Haldane and Rezai actually, using analogy, made a similar ansatz on a torus. So key point of Laughlin was that he wanted a function with vanishing along of diagonals. It was his ansatz, and Haldane and Rezai made the same, but on a torus. Well, but still there is a question of uniqueness. So what is going on here? And actually it was kind of clear to physicists all the time, but with my course, Semen Klevtsov from Strasbourg, we worked for a long time, well, on mathematical foundations of that. And the mathematical observation is the following. So firstly, these wave functions of Haldane and Rezai are actually wave functions of n body system. So what is written here? So I have an abelian variety A, which is a product of n copies of my torus. On my torus, I have a line bundle, and then I take exterior tensor product of line bundles. Now degree is m times n, and there is some moduli parameter. So the ground state of one particle is a space of holomorphic sections, and the ground states of an n particle system is a tensor product of the corresponding ground states. And another isomorphism is given just by Q-net formula. So we say with Semen that wave functions of Haldane and Rezai are actually wave functions of n particle systems on a torus. Well, actually in the sense I just said. So we have a particle system, and we can speak about the ground state. But we do not take all wave functions, but only those which have vanishing of order at least m along of each diagonal device. So actually, we follow the recipe of Laughlin. Well, and say for us only those wave functions matter which vanish along of each diagonal. And then the conclusion is, well, the function, the space Haldane and Rezai wanted to look at is precisely the space, well, I give. So it is in particular m dimension. And it can be understood as the space of sections of this line bundle, exterior tensor product of line bundles, listed by some device. And it can be continued since the line bundle we want to understand has another description. So it is a pullback of another line bundle with respect to the map mu, which is a very natural map. So the map mu assigns to a tuple of points on my abelian variety they sum. Now, again, an exercise in algebraic geometry makes it clear that the pullback, the global sections of the pullback can be identified with global sections of line bundle we want to pull back. And now I want to proceed slightly to the result. So what do we have? So we have an animpatical system. So we took a number m. There is a dependence xi, which enters actually in the spectral problem of one particle system. And we want now to make an assignment to a point xi of my torus to this vector space. We want to make from it a vector bundle. And well, on the physical level, it's feasible, so what is going on, but mathematically, so one has to work more hard. And the construction is provided by the introducing you the so-called Poincare line bundle. So Poincare line bundle is a unique line bundle on the product dual torus times torus, which is characterized by the following property. So if I take a point in my dual torus and restrict my line bundle, then I get a line bundle of degree 0 with a parameter xi, well, as a restriction. And if I take another norming, so it's another condition. So this vector bundle pi, this line bundle is actually unique. It's clear that it is unique, but also in this case, it can be easily described. So if I identify dual torus with the torus, then it is a line bundle attached to the divisor I just written you here. Now I have an exercise to attach to a point xi, this vector space. In a way, it becomes a holomorphic Hermitian vector bundle on my torus, or on a dual torus, if we actually more precise. And it is done via the following construction. So we have such a diagram of abelian varieties, projection, map involving the sum of points, and projection on another vector. And now we introduce vector bundle B obtained by the following procedure. So we take a line bundle of degree m on E, pull it back, tensor it with a Poincare line bundle on the product, pull it back again, and take the direct image. So these are some standard operations in algebraic geometry. And in general, it is just a coherent sheaf. But in this case, it's a vector bundle satisfying the following properties. So it can be checked that this vector bundle is stable of rank m and degree -1. Fiber, so these vector bundles are just wave functions of Haldane and Rezai. Quite strikingly, a most complicated part of the story is to show that the canonical connection of this Hermitian line bundle is projectively flat. So it's actually very important for physics. And since my time is running up, so let me say you that the proof involves Fourier-Mukai transforms. So summary of what we have done. So we constructed vector bundle B. with this invariance, rank and degrees -1. Fibers of this line bundles are given by wave functions of Haldane and Rezai. The bundle is stable, and actually it's quite interesting and also showing that this model makes a lot of sense, is that this bundle does not depend on the number of particles n. So its metric depends, as it should be, but the bundle itself does not. And actually the key point, and I do not have time to explain it, but it does not come out of the blue, is that the slope of this bundle is actually the whole conductance of my system. So actually I wanted to tell you that the whole conductance of electron system take discrete values, which should be fractions, and there is an explanation telling you that, well, indeed we have to take the slope. Well, and it's a story. So this story has a continuation because we also want to implement other fractions. And to do it, one has to speak about the model of Keskive-Curie and Venn, which generalizes the model of Haldane and Rezai. So the corresponding mathematics is very interesting. So it involves a theory of Fourier-Mukai transforms of on a billion varieties. But, well, my time is over, and I would like to thank you for your attention.